Hello, everybody. This is Bert Dixon here presenting for Math 40 statistics on section 4.3 and 4.4. Section 4.3 is going to cover the multiplication rules and conditional probability. And then section 4.4 is going to cover the counting rules. And again, you will not be required to write any of this down. That's up to you if you want to take notes on this, except for the student notes portion of the document that I have shared with you in Canvas, as well as on my assignment grid. So the first probability rule says if two events are independent, by independent we mean one event does not impact the other. So for example, if you flip a coin and then you spin a spinner, the outcome of the coin has no impact on the outcome of the spinner. And so those would be examples of independent events. The outcome of one does not impact the outcome of the other. A case where events are not independent, that would be dependent events. So, for example, if you had a bag full of different color marbles and you pulled one marble out and you didn't put it back in, then this probabilities on the second draw would be dependent on the marble that you pulled out on the first draw. And so those would be examples of non-independent events, or in other words, dependent events, if you took something out of the bag and you didn't put it back in. So we'll deal with that a little bit later, but right now we're assuming A and B are independent events. And so the probability that A happens and B happens is just simply the probability of A times the probability of B. The word and is sometimes denoted using this symbol. That's a set notation symbol. So when you see that what looks kind of like an N, that is that means and. So when you see that, you say and so the probability of A happening and B happening. That's also called the intersection. So the intersection of event A and event B. So that N looking symbol, that's A intersect B. So A and B or A intersect B, those really mean the same thing. So for example, 1, if we flip a coin and roll a 6-sided die, those would be two independent events. So to find each probability, the probability that we get heads on the coin and we get 3 on the 6-sided die, that would be, since those two events don't have any impact on one another, that would simply be the probability of heads times the probability of 3. And the probability of getting heads on a coin is 1/2. There's one head out of two possible sides. The probability of getting a 3 on a 6-sided die is 1/6. There's only 1 3 on a 6-sided die. And so that gives us an answer of 1/12. The probability of getting tails and an even number, again, those are independent events. So we'd have the probability of tails times the probability of getting an even number on the die. Probability of getting tails is 1/2 on the coin, and the probability of getting an even number, 1, 2, 3, 4, 5, and 6. 2, 4, and 6 are even numbers, so 3 out of the 6 are even. That's the same as 1/2 times 1/2, which is 1/4. So the probability of getting tails and an even number is 1/4. This can also be represented using what we call a tree diagram. So if we do the coin first and then we do the spinner, we can see each of those outcomes here. So the coin is going to be a head or a tail. And so the coin event has two possible outcomes. The spinner, doesn't matter what happens on the coin, the spinner has 6 different possible outcomes. So we could get a 1, a 2, a 3, a 4, a 5, or a 6. And then the tail can also, after getting a tail on the coin, there are also 6 possible outcomes: a 1, a 2, a 3, a 4, a 5, or a 6. And so we see there are really 12 different outcomes. And when we spin a spinner, when we flip a coin and when we roll a die, there are 12 different possible outcomes that can occur. And we can even see the probabilities. The probability of getting heads is 1/2, and the probability of getting tails is 1/2. The probability of getting, sorry, this was not a spinner. This is a rolling the die. And on the die, we can get 1, 2, 3, 4, 5, or 6. So the probability of rolling a 1 on the die is 1/6. The probability of rolling a 2 is also 1/6. 3 is 1/6, and so on and so on. So if I want the probability of rolling heads and a 3, that's this outcome right here. So all we do is multiply these probabilities. 1/2 times 1/6. 1/2 times 1/6 equals 1/12. So the probability of rolling a heads and a 3 is 1/12. Same answer we got up here. And then the probability of tails and an even number. So here's tails and an even number. That would be this one, and this one. So again, these would all be 1/6, 1/6, 1/6. So that's 1/12, 1/12, 1/12. Add those together and you get 3/12, which is 1/4, the same answer that we got when we used the multiplication principle. Okay, in the next example, we're going to choose a random card from a standard deck of cards. A standard deck of cards is 52 cards. If you are not really familiar with what's in a deck of cards, you may want to buy a deck of cards and just take some time to study what's actually in a deck of cards. Not everybody plays card games like was the case necessarily when I was a kid, and even more so when my parents were kids. As the generations go on, it seems like fewer and fewer people are playing card games when they're kids because there are things like video games and a lot more other things to do, like watch TV and many other distractions. So people don't play card games as often anymore, but you do need to be very familiar with what's in a standard deck of cards for this course. And so, like I said, if you're not familiar with playing cards, at least be familiar with what's in a deck of cards. And so this lesson will make more sense if you do that first. So in this case, we're finding the probability of drawing a. We're going to choose a random card, and then we're going to replace it, reshuffle, and then choose a second card. So in this case, they're going to be independent events because we're putting the card back. And so the probability, the multiplication property still applies in this case because the first draw and the second draw are independent events because we've put the card back in and reshuffled. There's still 52 cards in the deck. So this is going to be the probability of red king times probability of club. And there are 2 red kings in a deck of cards. There's a king of hearts and a king of diamonds. And so there are 2 out of 52 red kings. And then clubs, there are 13 clubs in a deck of cards out of 52. So then if we multiply those, 2 out of 52 times 13 out of 52 ends up being, if you multiply those and simplify, you get 1 over 104. I'm going to show you something on the calculator. If you have a TI-83 or TI-84 and you do 1 divided by, let's see, I need to turn that on. Okay, so actually I'll back up a step, and what I did was I multiplied on the top here. 2 times 13 is 26. And then in the bottom, I have parentheses 52 times 52. And that gives me a decimal when I multiply those. And I want to be able to write that as a fraction. So once you get a decimal answer, you can just simply press math. And the first option that's already selected there is frac. So that's math frac, enter, enter. And it changes that decimal into an equivalent fraction if possible. It's not always possible, but in this case, the calculator is able to write that as the fraction 1 over 104. And so we can say that's 1 over 104, and it is also about 0.009615. So that is about 1%, 0.096, or about 1%, because this would round up to a 1, and so we're really close to 1%. So there's a 1% chance that you're going to draw a red king and a club in that order. Okay, and then the probability of drawing an ace on the first draw and an ace on the second draw. So the probability of drawing an ace on the first draw, there are 4 aces in the deck of 52. We put it back in, we shuffle, there's still 4 aces out of a deck of 52, and so that is 16 over 52 times 52 is 2704, and then that reduces to 1 over 169. And again, I can get that by doing 16 divided by 2704 gives me the decimal answer. But then if I go math, enter, enter, it changes it to the fraction 1 over 169. So we can say it's exactly 1 over 169. That is approximately 0.00592. So we'll call that 0.59%. So it's always good to write your probabilities as a fraction, as a decimal, and as a percent. So I have all 3 here. And then we'll move on to our second multiplication rule. In our second multiplication rule, this deals with when the events are dependent, and so there's some new notation here. When you see this vertical bar, we say given or given that. So the way this reads, this is the probability of A times the probability of B given A. And what that means is the probability of B happening given that A already occurred. And so whenever we see that vertical bar, we say given. So B given A or B given that A already occurred. And so we can see this in the next example. Here, we still have the same deck of cards, and we're still drawing 2 cards, but the difference is we're drawing the second card without replacing the first card. So now there's only 51 cards left in the deck by the time we get to the second draw. So we're going to look at the same 2 questions we did on the first one and see how those probabilities change. So the probability of drawing a red king on the first draw and a club on the second draw is going to be the probability of a red king times the probability of drawing a club, given that we already drew a red king on the first draw. And so that's what that vertical bar means. And so in this case, the probability of drawing a king, that's still 2 out of 52. There are 2 red kings in the full deck. And now we've taken a card out, and we know it's a red card, so it can't be a club. Clubs are black. And so the probability of drawing a club, all 13 clubs are still in the deck, but there's only 51 cards remaining. So now we get 2 times 13, which is 26, and then 51 times 52 is 2652, and 26 divided by 2652 is 0.009803, or if you do math frac, that is 1 over 102. So that is about 0.0098. Sorry, my stylus is not cooperating. 0.0098, so we'll call that about 0.98%. So again, almost 1%, but it's slightly different than what we got on the first case, which was 0.9615. This is 0.98. And then the probability of drawing an ace and then drawing another ace. This is probability of ace times probability of ace given ace. So that means given that we already drew an ace on the first one. So the probability of drawing an ace on the first one, there are 4 aces out of 52 cards. Now 1 ace is gone. We already took it out. We're not putting it back. So there are 3 aces remaining out of 51 cards. So then we get 12 over 2652. That reduces to 1 over 221, and that is about 0.00452. So we'll call that 0.45%. And then next we'll move on to conditional probability. And this is a formula that we can use to calculate conditional probabilities when you use that given that symbol. So the probability of A given B, remember when we see that vertical bar, we say given. So the probability of A given B is the probability of A intersect B, or remember when we see this, we can say intersect or we can say and. So the probability that both A and B occur divided by the probability of B occurring on its own. And so there are a lot of situations where you can use this formula, but you also may be able to reason through the probability without using this formula. And so I'll demonstrate that here with these next examples. I'll do them both ways so that you can see how it could be done with the formula or without the formula. Okay, so let's look at example 4. This table gives us data on how many people got headaches after taking a certain medicine versus how many got headaches if they didn't take the medicine. And so we want to find the probability of A given B. So it says here that A is the event that the participant did not get a headache. So A is going to be no headache. And event B is the event that the participant took the medicine. So took the medicine is event B. Okay, and we're trying to calculate A given B. So let's try it without the formula first. So without the formula, we already know it says given B. So we already know that they took the medicine. So we can ignore the rest of this table. We only need this information right here because we already know they took the medicine. So we're ignoring the rest of the people in the data. And so we know they took the medicine. How many didn't get a headache? So that we can see that right here. There were 54 out of 65 that didn't get a headache. And so that is 54 out of 65. And that is about, we'll say 83, maybe 83.1% to be a little bit more precise. 83.1%. Okay, so that was without even using the formula because I know that since it said given B that I could ignore the rest of the table and I could just isolate the given that column. It was given that they took the medicine, so I'm only looking at column B, or at the took medicine column, and I ignore the rest of the table. Okay, so now let's go back and look at it again this time. This is event B still. This time we're going to use the formula. I'm trying to erase this and it's just not cooperating. There we go. Okay, so using the formula, I could say the probability of A given B. The formula says that's going to be the probability of A and B occurring divided by the probability of B. And so the probability that A and B occur, so that's the intersection right here. That's where the took medicine and the no headache intersect with one another. And so that top value is 54 out of the 100 people that are in the table. The probability of B is the probability of people that took medicine. So how many out of the total population, how many people took medicine? 65 took medicine. So that's going to be 65 out of the whole survey, which is 100. And so then when we do the division of those two fractions, we just simply get 54 out of 65, which is again 83.1%. Same answer, but this time we use the formula instead of isolating a column or a row in the table. Okay, let's try example 5. And again, I'm going to try to do this just by standard reasoning. without the formula, and then I'll do the same thing with the formula so you can see how they will yield the same results. I would always prefer that if you can do something with kind of what you might consider common sense or just your mathematical intuition, that's better than memorizing a formula. But if you're not really seeing how you could do these without the formula, then by all means, use the formula. Okay, so in this case, standard deck of cards, what is the probability that a red card randomly chosen from the deck is a jack? So the probability of drawing a jack, given that it's a red card. So it says, what is the probability that a red card, so it's given that it's a red card, is a jack. So the probability of a jack, given that it's red. And so we want to think, so doing it without the formula, we just want to think, okay, how many, if we know it's red, how many red cards are there in the deck? Well, there's only 26 red cards in the deck. It's all the hearts and the diamonds. So half of the deck is red. And from that, there's a jack of hearts and a jack of diamonds. And so there are 2 jacks left in the deck of, we're down to 26 cards because we know we're only looking at the red cards. So that's 2 out of 26 or 1/13. Okay, so I did that without using the formula. Now using the formula, we would have the probability of both. So jack intersect red, that really means it's a red jack, divided by the probability of red. And so the probability of drawing a red jack, there are 2 red jacks in a deck of 52. There's a jack of hearts and a jack of diamonds. Probability of drawing a red card from the deck, there are half the deck is red, so that's 26 out of 52 or 1/2. So we have 1 out of 52 divided by 1/2. That would be, sorry, wait, yeah, that is, yeah, that's 1/2. And so we have, now when we do 2 divided by 52 divided by 1/2, that becomes 4 out of 52, which is 1/13. Same answer that we got when we didn't use the formula. Okay, and then I'll do the same thing with this last one, doing it both ways. What is the probability that a random jack drawn from the deck is red? So what is the probability that our card is red, given that we know it's a jack? So probability of red given jack. So it's the opposite of what we just did. And so now we know it's a jack. There are only 4 jacks in the deck. 2 of them are red, so that's going to be 2 out of 4 or 1/2. So I was able to do that pretty quickly without using the formula by just isolating, looking at, I know it's a jack, so forget the rest of the deck. I know it's a jack. There are only 4 cards that I'm looking at, and 2 of them are red. Okay, and then using the formula, we would have probability of red given jack is the probability of red and jack divided by probability of jack. And so probability of drawing a red jack, there are 2 red jacks in a deck of 52. And then the probability of just drawing a jack, there are 4 jacks out of 52. And so that is 2 out of 4 or 1/2. Same answer that we got without using the formula. Okay, so next we're going to look at how you calculate probabilities that are asking that at least one of something occurred. And we're going to use what we call complement probabilities in order to do this. So a single die is rolled 3 times. Find the probability of getting at least 1 5. So this is what we're talking about when you have a problem that says at least one, then it is possible to calculate this, but it would be a very long, tedious process, because what we'd be doing if it says at least 1 5, we rolled 3 times, so that means at least 1. That means there could be exactly 1 5. So the probability of 1 5, or the probability of 2 5s, or the probability of all 3 being 5s. So instead of calculating those 3 probabilities, it's easier to just say, what is the probability that none of this happens, and take the complement of that. So the complement means we know that the probability of all possible outcomes is 100%. So if we subtract the ones we don't want, then what we end up with is correct. So the probability of any event occurring is 1 minus the probability of A complement. So the A complement means that A didn't happen. So AC means that A does not occur. Okay, and so it's easier to calculate the probability that we don't get at least 1 5 than it is to calculate these 3 probabilities separately. So the probability that A happening is, in this case, going to be 1 minus the probability that there are no 5s. And so 1 minus the probability of getting no 5s means if you roll a die, the probability of not getting a 5 is 5 out of 6. The probability of not getting a 5 on the next one is 5 out of 6. And the probability of not getting a 5 on the next one is 5 out of 6. So we have 1 minus 125 over 216, and that ends up being 91 over 216, which is about 42.1%. So that's going to be our general strategy, is when we see a problem that says there's at least one of something, just do it as 1 minus the opposite of that. So the opposite of at least 1 is none. If there's not at least 1 5, then that means there were no 5s. And so that's what A sub C means. That's the notation we use for what we call A complement. So when you see A sub C, that means A complement, which means A does not occur. Okay, so you should be ready now to pause your video and do the student notes portion of 4.3 and 4.4, or at least for, sorry, you're just doing the 4.3 part right now. So if you pause your video, take out your worksheet, you're going to start at the one that says multiplication rules for probability, and you are going to go until you see this. You can ignore this. This was supposed to be attached to a different problem, but it's the problem that it's referring to is not here. So you're going to go until you reach I believe lab problem 11. Let's see, do I have anything after that? Yeah, so yeah, you can stop at lab problem 11. So you're going to continue on in your packet, and once you get to lab problem 11, go ahead and do that, and then stop. And then you can continue on with this video. So you're just pausing your video, doing the student notes portion, which you'll submit later on after that chapter 4 packet's all done, and then press play when you're ready to continue with this lesson. So now we'll go ahead and work on lesson 4.4, which is on the fundamental counting rule, which is also known as the fundamental counting principle. And so that basically says that if you have events that occur in many different ways, then the total number of possibilities is the product of all of the ways that those events occur. And so you can read this, but it's probably going to make more sense if I just do it as an example. So we have, in this first example, we have 4 different shirts we can choose from, 3 different pairs of pants we can choose from, and 2 pairs of shoes that we can choose from. So we want to know how many different outfits can we put together with 1 shirt, 1 pair of pants, and 1 pair of shoes. And so all we have to do is make spaces for our 3 things. So this will be our shirt, this will be our pants, and this will be our shoes. So we have 4 different options when we choose our shirts. We have 3 different options when we choose our pair of pants, and we have 2 different options when we choose our shoes. So that is 4 times 3 times 2, which is 24 different ways that you can get dressed. So that's basically what the fundamental counting principle or the fundamental counting rule is that you can just multiply the ways that things can occur, and that gives you the total number of possible outcomes. So in example 2, this time we're making a license plate frame, or a license plate with 3 letters followed by 4 numbers. So we have 1, 2, 3 letters followed by 1, 2, 3, 4 numbers. So these have to be letters. So we have 26 letters in our alphabet. And then these have to be numbers. So these are going to be digits 0 through 9. And so since there are 26 letters in our alphabet, there are 26 choices for that spot, 26 choices for that spot, 26 choices for that spot, 10 choices, 10, 10, 10. And if we multiply all of those out, we get, let's see, 26 to the third times 10 to the fourth. That is 175,760,000 license plates. So that, again, is an example of the fundamental counting rule. There is a second part to that question, and it says, what if no repeated characters are allowed? So if we're not allowed to repeat any of the characters, then there are 26 letters for the first choice. Then we've already used 1 letter, so there are only 25 letters remaining, and then there are only 24 letters remaining. And then the same thing with the digits. There are going to be 10 different digits available. Once I've used a digit, there are only 9 remaining. And once I've used another digit, there are only 8 remaining. And when I've used another digit, now there are only 7 remaining. So if I multiply them now, I get 26 times 25 times 24 times 10 times 9 times 8 times 7. And that is 78624,000. So that's 78,624,000 license plates. That's if we don't allow any repeated characters. Okay, and so this leads us into another method of counting, and that is when we're looking at permutations, we're looking at the number of arrangements, the number of ways that we can arrange a set of objects or letters or numbers or something like that. So for example, the letters A, B, and C, I can arrange them a lot of different ways. I can do A, B, C. I can do A, C, C, B. Those are the combinations that start with A. and then the permutations that start with B, BAC, BCA, and then I can do the permutations that start with C, so CAB and CBA. So there are 6 different permutations of the 3 letters A, B, and C. Another way that we can see that is by the counting principle. How many ways can I fill this spot? Well, there are 3 different choices. Once I've put a letter there, I only have 2 letters remaining. And once I've placed letters in the first 2 spots, I only have 1 letter remaining. So when I multiply those, that's 3 times 2 times 1, which is 6. Now, when you count down in numbers like that, 3 times 2 times 1, another way to say that is 3 factorial. So when you see that exclamation mark, you say factorial. So the number of ways of permuting 3 items is just 3 factorial. And you can also do that on your calculator. Your calculator has a factorial button. Let's see. There we go. All right, so on the calculator, factorial is under the math menu. So if we wanted 3 factorial, 3, even though we know it's 3 times 2 times 1, we would do 3 math probability. So you can scroll over to the probability menu, and then factorial is the 4th option down. So you can either scroll to it or you can type the number 4 and it'll jump to that. And so 3 factorial is 6, just as we calculated here. Okay, so again, that was the math probability menu, and I'll show you that again several times during this lesson. So list all the permutations of the letters in the word home. So there are many of them. So HOME is one. So that one starts with H and O, and then we could do HOEM. And then I could look at ones that, what if we do HM, then we could have OE, and then HMEO. So those are all the ones that start with H and M. And then how about HE? Then I'd have OM or HEMO. And so now I've got 6 different permutations that started with the letter H. I could do the same thing with all the ones that start with O. So OHME, OHEM. Then I could do OMHE, OMEH. And so I did the ones that start with O and H, the ones that start with O and M. The only one left is the ones that start with O and E. So that leaves MH or OEHM. So notice that we got 6 that started with H, 6 that started with O. So naturally there's going to be 6 that start with M and 6 that start with E. So you can try those and see if you can get them. So it's 6, 6, 6, 6. There are 24 altogether. We can also see that using the permutation method. There are 4 different choices for the first letter, 3, 2, 1. And 4 times 3 times 2 times 1, that is just 4 factorial. And 4 factorial is also 24. So there are 24 permutations of the letters in the word home. I showed you 12 of them. Those are the ones that start with H and the ones that start with O. You can see if you can come up with the other 12 that start with M and that start with E. So let's say we had a word with 7 letters, or if we wanted to create a number with 7 numbers. How many permutations are there? To arrange 7 numbers, that is just going to be 7 factorial, which is a really big number. We don't want to try to list them, but if we use if we get help from our calculator here, we can just type 7 math probability, option 4. This time, instead of scrolling down, I'm just going to press 4 on the keypad and it jumps to option 4. 7 factorial is 5040. Okay, so those are just standard permutations. Now, in the next example, in example 3, we have repeated letters. And so since there are 2 S's, we're not going to get as many permutations here because if I switch those, it still looks the same. So it's going to be 4 factorial to start with, but then we realize that half of them, you could just reverse the s's and it would be the same. So we're going to divide by 2 factorial. And so that is 24 over 2, and that is 12. So in general, when you have repeated items, you just do the number of letters factorial in the top and the number of repeated items factorial in the bottom. So for example, in the word SASS, we have 3 S's. So we could say there are 4 factorial ways to arrange those 4 letters, but since 3 of them are repeated, they're going to look the same when we arrange those 3 letters. And so it's 4 factorial divided by 3 factorial, which is just 4. Now that's a really low number, so you might be wondering, how can there only be 4? Well, because there are 4 different places that we can put the A. So we could do ASSS, we could do SASS, SSAS, or SSSA. There really are only 4, and the permutation formula or the factorial formula gives us that same answer. So now let's look at a harder one. Mississippi, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So it's 11 factorial, but then we have some repeats. We have 4 S's, so we're going to divide by 4 factorial. There are 4 I's, so we're going to divide by another 4 factorial. And there are 2 P's, so we're going to divide by 2 factorial. And so if we multiply all that out on the calculator, it's going to look like this. You have 11 factorial, so 11 math probability option 4 divided by, now I need to put all the stuff that's in the bottom in parentheses. So I'm going to divide by 4 factorial times another 4 factorial times 2 factorial. Now 2 factorial is just 2 times 1, which is 2. So I'm just going to type times 2, close the parentheses, enter. There are 34,650 ways to rearrange the letters in Mississippi. Okay, moving on. The next example, we have a 4-digit bike lock, and each digit can be the numbers 0 through 9. And so how many different 4-digit permutations are there? So 1, 2, 3, 4. There are 10 choices there, 10 choices there, 10 choices there, 10 choices there, and that is 10,000 different permutations. So the probability of guessing the right combination, there's only one right combination out of the 10,000 in our sample space, and so we just get 1 over 10,000, which is 0.0001. And that is 0.01%, very small. How many different codes would there be if no digits may be repeated? So if we don't allow repeats, then there would be 10 choices for the first one, 9, 8, 7. And so you can multiply that out on your calculator easily, 10 times 9 times 8 times 7. But if this was a bigger problem, you wouldn't want to have to write out all of those every time. So another way to do this is to use the permutation notation, which is we have 10 numbers. We're going to permute 4 of them at a time. So 10p4 means 10 numbers. We have 10 different digits, and we're permuting 4 of them because we're not allowing any repeats. So 10p4, this notation, NPR for permutations, if we have n items and we're permuting r of them at a time, the formula is that is n factorial over n minus r quantity factorial. So in this case, 10p4, we would do 10 factorial, and we would divide by 10 minus 4 factorial. So that's 10 factorial divided by 6 factorial. And if you do that on your calculator, 10 math probability option 4 divided by 4 factorial, 4 math probability option 4, 10 factorial divided by 4 factorial. Sorry, that was supposed to be a 6 factorial. I'm just going to go second enter, is supposed to divide by 6 factorial, not 4 factorial. So 10 factorial divided by 6 factorial is 5,040. Same answer. As we got by doing it by the fundamental counting principle method. Okay. Also notice that on your calculator, I can do 10p4 directly. Watch this. On the calculator, if I just type 10, I go to math, probability, but instead of going to option 4, look at the second option down that says NPR. So if I type NPR, 10 NPR 6, or sorry, 4. So 10 items, we're permuting 4 at a time to get our 4-digit lock code, and it says that is 5,040. So the same answer, 3 different ways. So you'll use that permutation item on the calculator whenever you want, or you can just use the formula and do it this way every time. Okay, so that's the next one is the next problem is related to that. So if we have 10 people, 4 boys and 6 girls in my class that volunteered to be a representative, I need 1 representative and 1 alternate. How many ways can I fill those 2 positions from the 10 volunteers? So that would be we have our 2 positions. There are 10 different people I can put there. Once I put somebody there, there's only 9 people left to put there, and so that is 90. If I draw the names from a hat to fill the positions, what is the probability that David is chosen as the class rep and Lindsay is chosen as the alternate? So that is only one of the permutations, and there are 90 permutations altogether. And this could also be written as, by the way, instead of writing 10 times 9, I could have said there are 10 people, we're permuting 2 of them. The order matters because having David as the representative and Lindsay as the alternate would be a different permutation than having Lindsay as the representative and David as the alternate. Okay, so 10p2, if you do that on your calculator, you'll see that's also 90. So 10 math probability option 2 NPR 2 10p2 is 90. There are 90 ways to permute 2 people. Okay, and so what is the probability that the class rep is a girl and the alternate is a boy? So here we'll go back to the fundamental counting principle. If we want to fill the first spot with a girl, that would be, there are 6 girls, so 6 different options for filling the first spot and 4 different options for filling the alternate spot. That gives us 24 permutations. So here the probability of David and then Lindsay is 1 out of 90. That's one permutation out of the 90 possible permutations. Okay, now moving on from permutations, we're getting into combinations, and so I want you to consider these 2 problems. I'll just take a minute and read 1 and 2 and see how does the wording differ. So what you might notice is that in the first one, they have 3 specific positions: president, vice president, and secretary. They're different jobs. So putting people in different positions is a different arrangement. Whereas for problem 2, we're picking 3 people, but we don't have 3 specific positions. They're just on a committee. So the order doesn't really matter in problem 2. So here for problem 1, the order matters. And when the order matters, we do a permutation, because that's what a permutation is. It's the number of different ways to rearrange the order. When the order doesn't matter what order we pick these 3 people. Order does not matter. We call that a combination. It's just a combination of people. The order doesn't matter. So that's called a combination. And so here we can say we have 5 people. We're permuting 3 of them. And so that is going to be 5 factorial over 2 factorial. And that is 5p3 is 60. So there's 60 different ways for that to happen. Whereas for the committee, this time we're just doing a combination, and there are going to be fewer because the order doesn't matter. So that is 5 people. We're doing a combination of 3. And this word C, it's kind of cumbersome to say 5 combination 3. It doesn't really roll off the tongue nice, and it doesn't really make sense. So whenever you see the C, instead of saying combination, say choose, because it makes more sense in terms of the problem. We have 5 people. We're going to choose 3 of them to be on the committee. And so even though the C technically stands for combination, if you say choose, it makes a lot more sense. 5 people, we're going to choose 3. 5 choose 3. We can do that the same way on your calculator, except we're going to choose the third option. So 5 math probability. The third option is NCR, and that is 5 choose 3 is 10. So if the order doesn't matter, there's only 10 committees that we can form. If the order matters because we're putting them in 3 different positions, we use a permutation, and there are 60 different permutations. By the way, the formula for NCR is n factorial over r factorial times n minus r factorial. So it's very similar to the formula you used for NPR, except you have this extra little piece right here. Okay, so that's the formula for NCR. So you use permutations when order matters. You use combinations when order does not matter. So let's look at this example. In a club, there are 8 women and 3 men. How many ways are there to form a committee with 4 men and 2 women? We have 8 women. We're going to choose 4 of them to be on the committee. And so that's how we're going to fill the first 4 positions. And then to fill the last 2 positions, we have 3 men. We're going to choose 2 of them to be on the committee. And so 8 choose 4, 8 math probability, 8 choose 4 is 70. And 3 choose 2, let's do this one using the formula. That would be 3 factorial over 2 factorial, 1 factorial. And that is just 3, so 70 times 3 is 210. So 210 different ways to form the committee with 4 women and 2 men. Okay, so now you should be ready to do the rest of the student notes for chapter 4. You've got some formulas on conditional probability. This Bayes theorem formula is a formula, again, a formula that you can use, but in a lot of cases, just like the examples I showed earlier in this lesson, you'll be able to find these probabilities without using Bayes' theorem, just by using reasoning, like in the examples I showed, how you can do a lot of these problems without the formula. But just be aware that that formula does exist, and you can use it if you ever need it. And so you're going to start your student notes there, and you're going to stop when you get done with lab 9. So the Bayes theorem and conditional probability formula is where you start, and then you're going to end at lab 9. So that's it for lesson 4.3 and 4.4. You can go ahead and finish up your chapter 4 packet and then submit pics in Canvas. Have a great day.